We'll resume our discussion on policy iteration algorithms that we were discussing in the previous lecture. So the only thing that we need to discuss from the previous lecture is the lambda policy iteration algorithm. Which also referred to as TD lambda. So TD lambda is more of a simulation based algorithm, and lambda policy iteration is sort of the theoretical framework for that algorithm. So remember what our job was. So we have an actor, we have a critic, you give a policy. So actor generates a policy mu k, gives it to critic. The critic either generates v mu k or jk and gives it back to the actor, and then the actor updates the policy mu k plus 1 and so on and so forth, right? So this is what our framework was. So critic evaluates the policy and actor comes up with a new policy, and we had given two notations: t mu of j equals to summation, this is over all j, this should be a function of I, c I mu I j plus alpha I'm just writing the notation because I wanted to make sure that this is there on the board when we need it. And so T maps are S2 RS, T mu maps RS2 RS, and M maps RS2 the policy space. Have we given a name to policies? Actually, we did not, but the policy mu from S to A. This is script M. This is script M, and these are the Bellman operators. So we have used these three notations in the previous class. So I'm just recalling those notations. And I wanted to make sure that we remember what we were doing in the previous class. One of the things we talked about in the previous classes, as long as so if actor is optimizing the policy according to the critic's evaluation, then you always come up with a policy which is strictly better than the policy that was used for the evaluation by the critic. So we are kind of sort of in that domain right now, except that in the case of lambda policy iteration, instead of evaluating the policy exactly, we are going to do an approximate evaluation of the policy, not a true evaluation of the policy. And even in that setting, it actually converges to the optimal solution. Okay. So what was the framework in the previous class? Let me remind you. So we defined what is known as a temporal difference. dk of ij is given by c I mu k I j plus alpha jj jk minus jki. And I am going to output jk plus 1 equals to jk plus delta k, where delta k is going to be defined as so this is the cost that I'm going to accrue with policy mu k. This is the future value that I'm going to accrue. So this jk is the output of critic at the kth iteration. Mu k is the policy that I'm trying to evaluate at the kth iteration. And then I'm going to subtract jk of I. So this is the temporal difference. This is the cost accrued, and I'm subtracting the current cost at state I. This one is at state j. J is the future state. Remember, right? So j is the future state. So this gives me this matrix, an S cross S matrix, dk. And then if I take this discounted, so remember lambda is between 0 and 1. Where should I write it? Maybe I should write it here. Lambda is a parameter that anybody can pick between 0 and 1. Maybe 0 and 1 can be included. Okay, so I'm picking this lambda, and you can see that the discount factor here is now a function of both alpha as well as function of the lambda that we have picked. So even if alpha is 0.99999, I can pick lambda equals to 0.5, and I can make this term as small as I want to. This discount factor can be as small as I want to. And this turns out to be beneficial when we are doing policy evaluation for very high discount factor problems. That's when the temporal difference method actually makes perfect sense. When you have alpha which is very, very close to 1. You want to discount further the policy evaluation part, because remember, our goal in any of these algorithms is to get to mu star. I don't care about these intermediate jks that the algorithm spits out. Right? So we want to get to mu star as soon as possible. That's our ultimate goal. So in value iterations, we were computing the value vk at every point of time by iterating on t. And then eventually we get the policy mu star by looking at v star and then solving for the one-step update. So in all of these algorithms, I don't care about vk, I don't care about jk. All I want to do is make sure I converge to mu star at some point of time in the future. So that's why in this particular algorithm, we are not doing exact evaluation, we are doing a approximate evaluation to get there. Yes?
So if you choose lambda equals 1, does it become exact?
Yes, so it turns out that for lambda equals to 0, this is value iteration algorithm. For lambda equals to 1, this is a policy iteration algorithm. And then for in between 0 and 1, you have something in between value iteration and policy iteration. Any other question? Yes.
Is there any cost related to the small lambda? Like lambda is like too small.
So if you're picking lambda equals to too small, you're essentially doing value iteration algorithm. So it's always good to have more parameters to play with. especially when you are in a simulation based setting. So right now we are talking about deterministic algorithms, but towards the later half of this course, we'll switch to simulation based algorithms, and there some of these terms becomes very important. So lambda would be a parameter to control the variance in your temporal difference estimate later on when we talk about TD lambda algorithm in the simulation based setting. But right now this just looks like a parameter that is artificially attached to this algorithm. Okay, any other question? Many a times in algorithm design, you want to have some parameters that you can tune, because then it allows you to control certain parts of the algorithm in the future. Okay, so it's similar to that. Okay, so let's see what this jk plus 1 turns out to be, right? So I get this jk plus 1, it's a function of state, which is previous jk plus this delta k. Delta k comes at, delta k is defined in this particular fashion. So I start with I0, I run this iteration for infinite amount of time, I compute the expected value of this discounted sum, that gives me delta k at I0. I do it for each state I0. So for each initial state, you do it, and then you get something which is a function of state, and then you add the two up, you get jk plus 1. So the question is, what exactly is jk plus 1? Okay, what is this thing? And it turns out it's a fixed point of a very specific contraction operator. So I want to derive that contraction operator for which jk plus 1 is a fixed point. So let's do that. The reason why I'm trying to derive it is because it gives you an idea of how to do analysis of algorithms of this type. So actually it's a very cool, I find it really cool. But maybe let's see. So how do you decompose this delta k? Like, can you guys come up with an idea of how do we decompose delta k? Like, is there something cool about this function? Some recursivity that you can think of? Yeah, you're right, but let's look at it. There is some recursivity involved here. So I have delta k of I0 equals to expected value of, I'm going to do some rearrangement of terms, I0 I1 plus alpha lambda times summation t equals 0 to infinity alpha lambda raised to t dk of I t plus 1 t plus 2. Given I0. What is this term? So see, it looks something similar to this, except that the ITs are shifted by one time step. So what is this summation? Actually, maybe let me try to write it in some other way. So this implies that delta k of I0 is expected value of dk I0 I1 plus alpha lambda expected value of this summation t equals 0 to infinity of this thing given I1 given I0. So I'll have two expectations here. Let me put two expectations here. So I have an inner expectation where I take the condition on I1, and then I have an outer expectation where I condition it on I0. Okay. The reason why I can do that is because this is a Markov chain. Okay, so technically I should be conditioning it on I1 and I0, but because it's a Markov decision process, it's a Markov chain. So all the future states don't depend on I0 because I've already conditioned it on I1. So there is something. So that's why I'm not writing I0 here. But technically speaking, I should be writing I1 comma I0, but then I know that the thing inside the expectation is only dependent on I1, not dependent on I0. What is this term? Yeah.
While running the algorithm, does the I0 depend on is the first value, or is it the parameter set from the previous initialization from the previous iteration or something?
So this I0, I'm going to pick all states. So I'll pick, so let's say you have n states. So I'll pick I0 equals to 1, do this whole infinite horizon simulation, compute the expectation. Then I'll pick I0 equals to 2. I'll do the same thing. Then I'll pick I0 equals to 3. I'll do the same thing.
And I1 will be the future state.
I1 will be the future state. So starting from state I0, what is the future state you will reach? Yes.
So you don't want the sum in the bottom expression.
This sum?
Yeah, because you have now two infinite sums.
I have only one infinite sum, right?
Because you plugged in the one above it. See how you drew the brace, the under brace? The under brace brings in the sum above, and now you have two infinite sums.
Do I have two infinite sums? No, I have only one infinite sum here.
Looks right above.
Above?
Yeah, you're,
Oh, I see. Okay.
you just don't.
Yeah, maybe.
get
Okay,
rid of the
maybe
bottom.
yeah. I erase this part, so then the entire sum comes here. Okay. So remember that this term is actually exactly delta k of I1. Okay, so that's the recursion I was referring to. So what I have is delta k of I0 equals to expected value of dk I0 I1 given I0. I think I need to condition it on I0 and plus alpha lambda times expected value of delta k I1 given I0. And I'm going to write it as P mu k times delta k. And I'm going to define this as b bar k of I0. So let me tell you what is happening here.
K is the number of iterations.
Can you say that?
K is the number of iterations.
K is the iteration number, that's right. So I'm at the kth step of the lambda policy iteration algorithm. So remember, in all these policy iteration algorithms, there is an outer loop of k, and then there is an inner infinite loop of t goes from 0 to infinity. Okay.
I guess we need a bracket around the p times delta, right? 'Cause that's,
Yeah, I mean, you can think of it as a matrix multiplied by a vector, and then I'm looking at the I0th component of that vector.
So the brace contains the alpha times the lambda or not?
I mean, alpha times lambda is definitely here. So this is delta k of I0 equals to d bar k of I0 plus alpha lambda times this. Okay, so now I'm going to put everything in a vector notation, so that way I don't have to write about I0 and I1 and all that stuff. So what I get is jk plus 1 minus jk equals to d bar k I0. Okay, maybe I need to tell you what d bar k of I0 means. So let's do that. Let's try to simplify this further. What does this imply? Summation p ij mu ki. This summation is over all j. C I mu ki j plus alpha jkj minus jki, and this is the same as T mu k jk minus jk. So this is the vector notation. This is for each specific I0. I0, 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 I0. Okay, so d bar k is given by this expression, and this side is given by this expression. So now I can collect these terms together, and what I want to tell you is what jk plus 1 is a fixed point of. That's what we are getting to. Okay, so we have a whole bunch of equations there. So I know that delta k equals to jk plus 1 minus jk. Which is equal to T mu k jk minus jk plus alpha lambda P mu k delta k. And this is equal to, so delta k equals to jk plus 1 minus jk. So I'm going to do the same thing. I have T mu k. I didn't do anything. Okay, we need to simplify things. What do I get now? I get that jk plus 1 Can I simplify it further? Can someone try to simplify it further? I want to convert this into things that I already know. I know this map, I know this map, I know this map. So I want to convert that into the maps that I already know. So what can I do? How about I add lambda c mu k minus lambda c mu k. So I added and subtracted a vector. Okay, I can do that. Do we see something? Do we see a pattern? So I'm going to collect this term and this term together, and I'm going to collect this term and this term together, and what I get is jk plus 1 equals 1 minus lambda t mu k jk plus lambda t mu k jk plus 1. Okay, so we are not necessarily evaluating the policy mu k, but we are certainly converging, getting closer to the value function of mu k, and jk plus 1 in specifically here is a fixed point of this particular operator. It's a fixed point of this operator, and what we are doing in lambda policy iteration is computing the fixed point of this operator, then updating mu k plus 1, then computing the fixed point of this operator, then computing mu k plus 1 again. And the main result in Bertsekas, so Bertsekas proved this result back in 1990s, proved that this particular algorithm converges to mu star eventually. Yes.
I'm a little bit confused about how we erase the alpha here.
How did we?
How did we erase the alpha?
Alpha, because alpha is part of the operator here.
Okay.
So alpha gets multiplied to jk plus 1, and then we have this mu k, right? So this is, what is t mu of j? It's c mu plus alpha p mu j. In the matrix format, this is how you would write it, right? This alpha gets absorbed in the operator t mu. Okay, and this operator has a contraction coefficient of alpha lambda. Okay, so remember, if alpha is close to 1 and you are applying a contraction map, it's going to take a lot of iterations to converge, but this operator has a contraction coefficient of alpha lambda. Under the soup norm, it has a contraction coefficient of alpha lambda, so we have artificially suppressed the contraction coefficient to get to jk plus 1 as soon as possible.
Are you evaluating T mu k and jk plus 1 if jk plus 1 is dependent on that?
So
it looks like you had an equation you have to solve.
So you start from mu naught, then you compute j1. Sorry, you compute j naught, then you compute mu1, and then you compute j1, and then you keep going round in circles. So I didn't quite understand what the question is.
Jk plus 1 depends on jk plus 1.
No, that's the fixed point of that operator. So jk plus.
Oh, okay.
So what we are doing is computing the fixed point of this operator. Okay, so let's define m lambda to be 1 minus lambda t mu k jk plus 1 minus lambda, sorry, plus lambda times t mu k of j. So what TD lambda, what temporal difference method or lambda policy iteration is trying to do is to compute the fixed point of this operator through an iterative process. And it turns out that that iterative process will converge because it's a contraction with respect to the contraction coefficient alpha lambda. So I've suppressed the contraction coefficient. Initially, the contraction coefficient was alpha for the general policy iteration or value iteration algorithm. Now my contraction coefficient is alpha lambda. So I'm going to converge to the optimal, to the fixed point very quickly in comparison to if I were to use lambda equals to 1. What happens when lambda is equal to 1? Then this term vanishes. You only have this term, and it just becomes a policy iteration algorithm. Okay, and when lambda equals to 0, then this becomes value iteration algorithm. Okay, so I'll just write it as a comment. So lambda equals to 1, standard policy iteration. Lambda equals to 0, standard value iteration algorithm. So that's the connection. So in all these different algorithms, we have the value iteration as one extreme, policy iteration on the other extreme, and then we are trying to figure out what's the territory in between. And so the modified policy iteration, enhanced policy iteration, and lambda policy iteration, all of these are the territory in between the value iteration and policy iteration. So think of it this way. So you have value iteration in one end, policy iteration in the other end, and in between you have enhanced PI, you have modified PI, and you have TD lambda. All of this falls somewhere in between by an appropriate choice of parameter. Yes.
It converges like more quickly.
That's a good question. I don't know whether it's a monotone operator or not. I'll have to think about it. So this is a fixed vector. T mu k could be a monotone operator if the cost functions are all positive. If the cost is all positive, so it could be a monotone operator. So in which case it might increase. Or maybe not. Yeah, let me take my comments back. I don't know whether it's a monotone operator or not. Okay. Any other question? So with this, we have come to an end of our discussion on the Markov decision processes. So we have studied, so within the umbrella of Markov decision processes, we have studied that stationary policies are optimal, deterministic stationary policies are optimal, value iteration converges, policy iteration converges. If you don't like value iteration and policy iteration, we studied 3 algorithms in between: enhanced policy iteration, modified PI, and TD lambda. They also converge. The problem with policy iteration algorithms is there is an outer loop of iteration, policy iteration, and then there is an inner loop of evaluation, right? So you have to evaluate the policy. So that's the drawback. But these are the algorithms. These are broadly the algorithms that are used to get to the optimal solution mu star asymptotically. Okay, so after infinite number of iterations, so remember in this case, you don't have one infinite number of iterations, you have infinite number of iterations. Okay, so after infinite number of iterations, you can converge to the optimal solution. Wonderful. So now let's get to the reinforcement learning side of things. So we talk about simulation based algorithms now. Okay, so far everything was known. I knew what the cost function is, I knew what the transition kernel is, I can actually evaluate these operators, and I'm able to solve the problem. Okay, many of these algorithms you will implement in your assignment too, so you will get a hang of how these algorithms are implemented. But the real problem is most of the problems that we are interested in would have extremely large state space, extremely large action spaces, and the transition kernel would be very complicated. Okay, so imagine if the number of states is 10 and number of action is 5. This is a very simple, easy to write matrix. I can write it on the blackboard. If the number of state is 1 trillion and number of action is 1 billion, there is no way on earth I can write it down. But in fact, there is no way on earth you can simulate it on a single machine. Okay, so you won't even be able to implement these algorithms on an actual computer, because the computer cannot have the memory that is required to evaluate these operators. Okay, so now we are talking about situation where these matrices are humongous, these cost functions are very large. I mean, in terms of storing it in the memory, it's very large, and evaluating these operators would take a very long time. Then what do we do? Okay, that's one part of the equation. The second part of the equation is, or the second part of the problem is, I don't even know what these PIJs and CIJs look like. Okay, so let me give you specific examples. So suppose I'm trying to play chess. Okay, that's one of the early success of reinforcement learning algorithms. So I'm trying to learn to play chess. How many states are there in chess? So that's basically the way the chessboard is arranged, right? So all possible ways by which the chessboard is arranged, very large number. Okay, so that's the state of the system. What's the action? How you are going to move the pawn inside that chessboard? So that's the number of action. So you have a large number of action, you have a large number of state, but you know everything is deterministic in that case. You know exactly how the chessboard is going to evolve if you take a specific action. Okay, so nothing complicated there. So everything is deterministic. And what is the cost function, by the way? Can someone tell me what's the cost in chess? So you either win or you lose, right? So you only see the cost at the end. In the intermediate step, there is no cost in chess. You don't pay any cost for making a move inside chess, but eventually somebody wins and that person reaps the cost of -1, and somebody loses and that person has a cost of +1. So that's pretty much. So you don't have a running cost, you have a terminal cost. Once you reach a terminal state, you get a terminal cost, and that's it. The chess ends at that point of time. So that's one example. The other example is Netflix example. So what is the state of the system there? So I want to personalize. I want to give a personalized recommendation to a user who is logged into my Netflix website. What's the state? Can someone tell me what the state in that problem is?
The last movie you watched.
What movies? So that's the history of observation. Do you want to make that as a state of the system? You can. I'm not saying that that's wrong.
Not like the history of movies, like the last one you watched.
Okay, so last one you watched.
Or the current movie that you are watching.
Yeah, okay. So the set of current movies that you're watching and the last one that you have watched. Okay, that could be one potential state of the system, but is that all? Can somebody come up with a different state of the system?
Like the category, like the movie you are watching.
Wonderful, the categories of the movies that you are watching. So you have the current movies you are watching, some past movies that you have watched, and the categories that you have watched. So you are increasing the state space. Any other?
Search engine history.
Sorry?
Search engine history.
So then you have to have a history is pretty long. So I've been a Netflix user for 12 years or whatever, 10 years. You can't have the history that is that long. Okay, yeah.
Me personally, if I've seen a movie somewhere else, I'll like click on it and upload it,
Huh.
even if I didn't watch it on the stream service.
Okay.
Uh,
So you are kind of reviewing the movies of some sort, even if you have watched it elsewhere, you're still reviewing it on Netflix.
so it's like not viewed on Netflix.
Right.
But it's uploaded.
Yeah. Okay, wonderful. You are doing a great service to humanity. Thank you so much for that. So he watches the movie elsewhere, and then he goes to netflix.com and then he writes a review for that movie or just says that he has watched that movie. So, yeah,
That could be like part of the state, like
that's part of the state. Yeah.
upload it or download it.
Right. Right. So definitely that's also part of the state. So essentially, the state space there is some combination of my personality, my likes, my dislikes, and my specific taste at that particular point of time. So if it is Friday night, I might want to watch a comedy movie, but if it is Sunday morning, I might want to watch a serious movie or a crime thriller or something like that. Right? So depending on the time of the day, my state of the mind also changes, my requirement for the taste changes. So that's actually the state, but you can never observe the state. There's no way to observe the state in that problem. But more importantly, there's no transition kernel as such. How does my taste evolve over time? Over the last 10 years, how has my taste evolved? There's no transition kernel that you can pick. What about the cost function? The cost function is whether I like the movie or not, whether it's 5-star or 0-star for me. Okay, so that's whether I've watched the movie all the way till the end or did I just watch it for 2 minutes and switch to some other movie. So it's a complex cost function. But in this particular problem, what happens is you can see the transition from IT to IT plus 1, and you can see the cost of IT to IT plus 1, but you never have a model of the system. So you have chess on one hand, where you have a very sophisticated model of the system. You can create a simulator that exactly simulates the chessboard. But then you have another system where all you have is a log data. I watched this movie at this point of time, and I watched it for 5 minutes versus 50 minutes versus I watched it until it was complete. So you have two extremes where, and we want to come up with algorithms that solves both these problems. Okay. So the way we are going to come up with algorithms is we'll pick one of these different algorithms, and then we want to figure out how do we do a simulation of this algorithm for a situation where we only have data set, but we don't really have the entire model. So remember, all of these operators requires you to fit all of this within the computer memory and to be able to execute the operator evaluation. But I don't have that possibility, and therefore I need to learn from data. And that's what reinforcement learning is about. Okay, any question on this? So let me try to classify reinforcement learning algorithms. So that way we know the landscape and where we are headed. So we have this broad field of reinforcement learning. There are two possibilities, model-based and then model-free. With a simulator or data. Model-based. Model-based. Okay. So think about model-based as chess, and in model-free, think about it as traffic simulator or Netflix. So this one goes back to 1990s. This one, I mean, of course, the theories were all developed in 1980s and 90s. And 19 or rather 2000 plus, we started having applications. Netflix, Google, Facebook, and so on. So the theory was pretty well known, but the application started coming in 2000 onwards. Okay. So within the model-based algorithms, we'll talk about asynchronous value iteration, and asynchronous policy iteration. Within the model free space, we have on policy, and we have off policy.
Model-based means that or you have an estimate of the PIJ, right?
Yeah, you might have. So model-based means that you know Pij and Cij. Even though you may not be able to fit it into a memory, you still know it. You know exactly what the cost is. And you know exactly what the transition kernel is, as is the case in chess. You know, I can tell you, show me the chessboard, show me the action you are going to take, and I'll tell you what the next state is going to look like. I know it, right? So that's model-based. Model-free means I have no idea of what the underlying model looks like. I don't have the cost function, I don't have the transition kernel.
But each step we get the reward.
You get the reward. Yeah, you can see the reward in the next state using the simulator or using the data, but you don't have the model of the system. Okay. So now on policy RL is, you are in a model free setting, you don't know what the model is, but you can change the policy as you wish. Okay, so that's on policy reinforcement learning. Off policy reinforcement learning is, you are seeing the data, but there is no way you can change the policy, but you still want to learn what the optimal policy is. So let's look at an example. You come to, so I'm New York Times, okay, or I am Wall Street Journal. You come to my website, I need to show you what news article you should read. Okay, now I can actually change the policy of the recommendation policy on the fly. Okay, it's in my control. I'm New York Times, it's in my control. I can change the policy. That's on policy reinforcement learning. I can show you some news articles, you don't like it, I'll change the news articles and show it to you again. So that's on policy RL. You are a doctor, you are seeing patients, there is a specific medical protocol that you need to follow. That's an off policy reinforcement learning. You still want to get the best treatment, you want to identify the best treatment for the patient, but you still have to follow the protocol until the protocol fails, after which you can change the policy. But in the beginning, it's an off policy reinforcement learning because you have to strictly follow the protocol. Off policy learning, reinforcement learning is also useful when I have historical data. So I have historical data of everybody who has had cancer so far and whatever treatments were prescribed to that particular patient. And based on that information, I cannot go back and change the policy, right? That policy was under some policy, that data was logged. So I have that information, but I need to figure out what the best treatment today is going to look like. So that's an off policy reinforcement learning. You cannot change the policy. The data set is coming from a specific policy. There is no way you can change the policy, but you still want to learn what the best policy looks like. So this one is typically useful in recommendation systems. Off policy RL generally wherever there is regulations involved. Regulations or risk. So there are certain risks or there are certain regulations that prevents you from changing the policy. So that's typically where off-policy reinforcement learning would be useful. Some of you might go to General Electric and you might work on a 500 megawatt gas power plant or coal power plant or some nuclear power plant. That's a highly regulated and risk sensitive environment. They have some policy, some control policy for running that power plant. But you might go there and you might want to figure out if there is a better way to control the power plant in order to get more from less. Okay, so that would be studied under the umbrella of policy RL. Okay, any questions so far? Yes.
Is one, so maybe in the context of like Gen AI, is one reason to use off policy because it's really expensive to.
So it's a good point. So Gen AI is actually, it's somewhere in between. Okay, so Gen AI would sit somewhere in between. So what they do is they first log the data from the users using a specific policy, then they update the policy, and then they release the next version. Okay, and then people will give it some review like good or bad or whatever, and then they'll change the policy and then they'll do it. So in some sense, they are doing a batched version of, so there's a off policy reinforcement learning because they collect the data over a batch, but then they do change the policy, and then that's roughly how they are functioning. So it's somewhere in between. It's not like they are changing the policy at every point of time. Like every day they wake up and they change the policy completely. That doesn't happen in Gen AI. Any other question? Okay.
Can I ask a question here?
Yes.
So like if we have data and we want to like infer some model, I don't know whether we can classify this into like model-based.
Yeah. So that would be somewhere in between here. So you have data, and then you do model fitting, and then you get policy. So an example of
Because wouldn't that also happen as you're doing off policy, or wouldn't you kind of need to implicitly build some sort of model?
That's right. So, but then the question becomes whether you have a parametric model already available to you. So I'll give you a specific example of this. So let's say when you are driving the vehicle, so one of the problem statements that we were working on is how do you pick the gear shifting of the vehicle? How do you optimize it using reinforcement learning? Now, the problem with gear shifting is we don't know in the vehicle how many passengers are sitting, so the mass of the vehicle is unknown. We kind of have some idea about 2,000 kilograms to 2,500 kilograms, depending on how many people are inside, but you don't exactly know what the mass of the vehicle is. And you also don't know what the intention of the driver is. So sometimes the drivers would want to rush to the specific point, so they would be driving pretty aggressively. But on other times, the driver would be pretty relaxed and they won't be driving aggressively. So there, if you don't know the mass, if mass is the parameter that you do not know, you can use the data to do some sort of model fitting to identify what the mass of the vehicle is, and then you come up with a policy that's best for that specific mass of the vehicle. Now you can, but if you don't know any, so the real value of off policy is like Netflix recommendation system kind of setting where there is no model, like it's not parameterized model that you already know. And many a times, PhD students and faculty and researchers in general would study a specific system like a battery, a lithium-ion battery, or growth of a tumor in order to come up with parametric models of the system. So initially, we don't know any model. We don't know how lung cancer progresses. But then there'll be like 20 people studying the lung cancer, the specific types of cancers, and so on, and they'll come up with a model of how the tumor grows, for instance, right? So then they come up with a model. There are some parameters in the model, and then you can do model fitting and come up with a policy. So sometimes you may start with no model, but over time, technology develops, knowledge accumulates, you have a model, parametric model of the system, and then you can move directly from off policy RL to model based RL. Okay, so that can happen, but it happens over decades. It doesn't happen overnight. Yes.
Is it better to have a model?
It's always better to have a model. And it's better to have a model because you become very sample efficient. So if you have a model, you can do this entire simulation on a machine and you can come up with the best chess playing strategy. Okay, it might take you $1 billion to figure out what the best chess playing strategy is, but you can do that. And then you can just execute that everywhere. Once you learn the policy, it's the best policy, you can execute it everywhere. When you don't know the model, it'll take you infinite amount of time to get to the optimal policy, right? So having a model is very good because then you can be extremely sample efficient. Like with 5 or 6 samples, you can maybe fit the model, and then you have a very good strategy to work with. Yes.
Speaking on and off, I think there is another 6 online and offline learning, right? It's different from.
It's the same thing, on policy and off policy.
It's online, offline, unflexible. They are same, right?
Yeah, they are same.
Oh.
Yeah. Online means you change the policy. Offline means you don't change the policy. Yeah.
So for that part, I go, compared to other methods, what reinforcement learning can give us more in when we want to create a big model that we believe is true?
Sorry, so you are saying that if...
Yeah, so like from data to model creating, like what reinforcement learning can give us compared to other methods? Like maybe it's...
Okay, so I think there is philosophy in reinforcement learning. So philosophy in reinforcement learning is I have data, I give it to a black box or whatever. Maybe I should not call it a black box. I give it to an RL algorithm, I get mu star. But if you ask Isaac Newton doesn't like this. Isaac Newton says, I'm going to collect data, then I'm going to think for, I don't know, 5 years or 20 years, and I get a model. And then based on the model, I do optimization. Okay. So to give you an example, suppose you wanted to send a rocket to space. Okay, that was your mission. You can keep building rockets and figuring out all the things, and you can try to figure out if it goes to space or not. And it might take you millions of years to get there. What Newton said, okay, there is laws of gravitation, F equals to mass into acceleration, and this and that. Then some chemistry people studied explosives, and then they figured out how to do controlled explosives and so on. So that became the propellant. And then some orbital mechanics people studied how things move around Earth and how things move around Moon and so on and so forth, building upon the information that Isaac Newton came up with. So there were a whole bunch of models for every piece of the subsystem within a rocket. Then you run the optimization, you figure out what's the best model for a rocket looks like, and then you build the rocket and, I don't know, go to space or do whatever you want to do with that rocket. Okay. So that's where model becomes very useful. So once you create a model, you have that model forever, and then you can keep doing optimization on top of those models. So like for instance, if you look at the current situation, like the current world, people are trying to figure out the model for cancer, people are trying to figure out the model for lithium ion batteries, people are trying to figure out model for materials discovery. We don't have good models for that. So people are trying to figure out good models for that. Maybe 50 years later, we will have good models for that. So right now, everybody is doing some sort of off policy or RL or on policy RL, and they are failing, but they are still writing papers about those failures. Over time, maybe in 50 years, we will have the models for how to discover new materials, and then we'll switch to model-based learning for those problems. Okay.
Another question is, even for off policy area, we're still interacting with an environment, right?
That's right.
So, and in theory, if we can interact with the environment, we can ultimately build a model.
Absolutely, for sure. So the question is, even in this case, we are interacting with the environment, Now, there are multiple types of environment. One environment is a specific cancer patient. You can interact in terms of talk, but you can't really prescribe them different drugs every day to figure out what drug works for them. Okay, so there are limitations to the interaction. The other side is Google. So I don't know, 3 billion people are making Google search every day. So they have 3 billion interactions every day. Maybe, so 3 billion is users. Maybe each user is using Google maybe like 5 times a day. So they have 15 billion interactions every day, and multiply that by 365. So they have so many interactions in a year, right? So the problem for Google versus the problem for doctors are completely different, even though both of them are interacting with the environment. Okay. Yes. Okay.
So reinforcement learning is kind of like performance like focused and like not about explaining the behind logic.
That's right. So reinforcement learning, the idea behind reinforcement learning is I look at the data and I compute mu star directly. That's the philosophy behind reinforcement learning. Depending on the problem, sometimes I would say this philosophy is good, as is the case in Netflix and Amazon recommendations. Sometimes this philosophy is bad. So if I were to optimize a hybrid vehicle, I wouldn't use this method, because I know for hybrid vehicles, every subsystem is very well studied subsystem. So I don't need to go from data directly to mu star. I can go from data to fitting the model to figuring out what the best policy is.
Sometimes like our prior knowledge can help our algorithm.
You should always, there is, wherever you have prior knowledge, you should exploit that prior knowledge. It might take you 1 month to figure out how to exploit that prior knowledge, but you won't fail during the reinforcement learning phase. So a lot of failures in reinforcement learning, maybe I'm making a pretty broad statement, but in many cases, the reinforcement learning fails because you tend to not use the information that is already available in the world. Okay, so there are multiple reasons why it fails. So one, sometimes it fails because you haven't defined the state space correctly, and sometimes it fails because you're not exploiting the entire information that is available. Okay. Okay. Cool. So let's get to the math. Back to the math. I'll introduce asynchronous value iteration and policy iteration today. Yeah. Asynchronous value iteration. So I have a set of states Sk that I picked in an IID fashion, and my Jk plus 1I equals to T Jki for I in Sk and Jki for I not in Sk. And I'm going to assume that all states are visited infinitely often. And I'll tell you what it means to visit something infinitely often. How many of you have seen this term infinitely often? Few of you? Okay. Okay, so I start from any initial value function, J0 or V0, whatever you want to call it. So start with any value function, and then you pick a set of random states, and then you update the value function for those states according to the Bellman operator. But For other states, you just let it be as it is. You don't change the state. You don't change the value function, so you get jk plus 1. You keep doing it. The only caveat is you need to visit all the states many times, infinite number of times during the process. So let's think about chess. We were planning to apply this asynchronous VI on chess, so I can evaluate this operator on a few states. During your lifetime, so I don't know how many of you play chess, but I'm pretty sure you guys play some sort of board game. How many of you think that you have visited all possible states that was possible on that board game? Right? Most likely not, right? But the convergence of this algorithm, this converges to V star as k goes to infinity, almost surely if you are visiting all the states infinitely often. So you are going to visit all possible states, not just once, but infinite number of times throughout the process of this algorithm. Yes.
Is that all states should be visited, or all state action pairs should be visited?
In this case, only states. You're only picking states.
Okay.
We are not talking about Q learning right now, but we'll talk about it in some time. Okay. So asynchronous policy iteration. I have jk plus 1I t mu k jk I in sk jk I not in sk, and then mu k plus 1I equals to m jki or jk plus 1I in sk, and the result here is if t mu naught j naught less than equal to j naught, then mu k converges to mu star almost surely. And I'm using the term almost surely here. I have not defined it. But I think people who have taken probability theory would know what almost surely means, and people who have not taken it, you can go and read it up on Wikipedia or something. Yes.
In the policy iteration, even though like you only update on some of J,
Yes.
you can still update all mu for all states.
Technically you can, but remember the problem is that I'm not able to fit all the states on a single machine. So I might have data centers all over the world which contains all the state and action information, and I might have to pool all that information in order to do the state or policy update. So that's why I'm going to pool only some amount of information and leave out all the rest.
But when you get the new k plus 1, you still need all information. I mean, you still need all the information from J k plus 1.
You are right, but typically what happens is you generally are able to figure out what information is needed in order to compute mu k plus 1. So for instance, if you're solving chess problem, there are only so many states that you will visit. So all you need to do is pool the information for those states, not all the possible states. I mean, implementation of these algorithms on actual hardware is a big problem in itself. And those are the people, by the way, who get $100 million paycheck from Facebook and Google. So people who know the theory, they remain poor. people who know how to implement it on GPUs and TPUs, they are the ones who are earning the money in today's market. Okay. So what you are learning is not as valuable as it would have been if you knew how to implement this on GPU. And just for your information, I know most of you probably wouldn't care about it, but we have faculty. For instance, there is Professor Tawfiq Musha in our electrical and computer engineering department. He builds high-speed Ethernet hardware. Okay, so circuits that are required for doing high-speed communication. Those are the switches that are used here. So he's, I think, testing something like 400 Gbps, 400 gigabits per second kind of Ethernet. Those are the kind of Ethernet that is needed to implement these algorithms. Okay, so you have everything within the department. It's just that it's all diffused. We have Professor D.K. Panda in CSE department who does high performance computing. So he figures out the hardware and server setup so as to execute algorithms of this type. I have no idea about it, so I cannot be helpful. But if you are interested, then you can go and take their courses. Okay. The third algorithm I want to talk about is, so those are the model based. So remember, we are using these operators. We should be able to evaluate these operators. And the only way you can evaluate these operators is if you knew what the model is, right? So let's move to model free method. Sorry, model free, yeah. So I'm going to go to model free algorithms now. Those are the only, I mean, there are many model based algorithms, but those are the two most common ones, so I'm covering them. This is not where most of the innovation actually happens. Like most of the innovation that has happened in the past 20 years is in the model free domain. So that's what we'll cover throughout the course. So the first one is Q-learning. So what is the setting here? I have a policy mu naught. Well, I have some policy mu. And either I have a data generating process or I have log data, which is I0, U0, I1, U1. Well, actually, C0, I1, U1, C1, and so on. Logged data means you have data from the past under some policy mu. So you have some policy mu and you have log data, which is I0, U0, C0. So the state, initial state, action, the cost incurred, next state, action, cost incurred, next state, action, cost incurred, and so on. So you have this humongous data set, infinite length data set, which you have logged from the past, or you might be actually generating it on the fly, doesn't matter. You are getting this data set under some policy mu. The only requirement is all state action pairs must be visited infinitely often. Okay, so this is different from saying that all states should be visited infinitely often. So now I'm asking all state action pairs should be visited infinitely often. So if you have 1 trillion states and 1 billion action, then imagine this 1 trillion cross 1 billion matrix, and you should be able to get to every point in the matrix infinite number of times. Yeah.
So is the policy unknown and you learn it from?
You don't need to know what this policy, what the data generating policy is. You don't need to know about it.
All you have to do.
Yeah, the only thing that is required for this policy is all state action pairs must be visited infinitely often. typically speaking, this assumption will be violated all the time, because you cannot come up with a policy that's going to visit all the state action pairs infinitely often. But for the theory to work, this is the assumption that we make.
So
Yeah.
the difference that here
Asynchronous.
Asynchronous, it only requires all states, and here for Q-learning it requires all state action pairs.
That's right.
So we already know the model.
That's right. We already know the model here. We don't know the model here. Okay. So the Qt plus 1 is updated as follows: 1 minus beta t of Qt IU plus So this is the update equation. So at every point of time, you update the Qt according to the previous value of Qt. This is minimum over all u prime that are admissible at the next state, given it plus 1 and u prime. So this is where some minimization effort is happening. You multiply that by a step size beta t. The beta t appears in two places. So this is how you update Qt plus 1. This update is only done for ITUT and not for other values of ITUT, not the other values of I and U. Okay. The requirements on the step size is, yes.
Sorry, so the top line depends on IT plus 1, which seems to be.
So this IU is IT and UT.
But inside the QT, there's an IT plus 1.
Yes.
So that means, I guess, at this time, you know IT plus 1?
Yes. So remember that the underlying assumption is you have the entire data set with you. So as long as you can have this information available at the time of updating Qt, you are good to go. The requirement on beta t is summation of beta t equals to infinity. Summation of beta t square should be finite. This is known as tapering step size. Okay, so we'll talk about it. We are out of time today, but we will talk about the convergence guarantee for Q-learning algorithm and why do we need this tapering step size. So we'll talk about it in the next class. But that's the Q-learning algorithm. That was one of the first model-free reinforcement learning algorithm, and I think discovered in 1970s or 80s maybe.
What's the meaning of tapering step size?
It means that summation of beta t should be infinity. Of course, beta t is greater than 0. So summation of beta t should be infinity. Summation of beta t square should be finite. That's called tapering step size.
It is TOP.
TA. Tapering step size. Okay, so we'll talk about Q-learning algorithms and other algorithms for model free in the next class. No class on Thursday, no class on Tuesday next week, no class on Thursday next week. So we'll have class 2 weeks from now.
Can you help us clarify what we have to do for the project proposal?
Let me send out an email. I'll send it out right after the class. Thank you.